Hi everyone, these are some Discover Materials resources that we've developed as part of the Porosity in Materials Outreach project. So as part of the Porosity in Materials project, we bought a lot of plastic play pit balls, and one of the things we did was put them in these Perspex boxes. So one of the questions you might ask is, how many balls are in this box? How might you work it out? That you might expect them to say 5 times 5 times 5 is 125, for example. Then, 121. We have these laminated cards so you can riff off that when you're speaking to the students or the teachers that might approach you. So, you've asked them about this box, maybe you've got an answer of 125, or if there's an approximate answer that isn't close to 125, maybe try and help them work it out. But then, if you think, whoa, they're really smart, well, get them to answer this one. So this is our second box. This has a lot of orange ping pong balls in it, and there's more of them. You might, from the previous box, get an answer that is, okay, they try and count them. So then they might do 8 times 8 times 8 and get a much greater answer, to which they'd be right. We have about 430 ping pong balls in this box. Let's compare how many balls we've got in each of these boxes. So, which one's got the biggest? The play pit balls or the ping pong balls? Well, the play pit balls, they're much bigger, so you fit less of them in. We said 121 play pit balls, whereas 430 table tennis balls here. So, the packing is very similar. They're both spheres. The total volume of balls in each of these boxes is very, very similar. But the number of balls is definitely different. We've got less here and more here. So if we think about the gaps that are between these particles, they are different sizes. If we've got the play pit balls, we've got slightly larger spheres, whereas the ping pong balls are smaller spheres. So the size of the gaps, or the volume of the gaps, is different. The volume of the gaps for the play pit balls, much bigger, whereas for the table tennis balls, smaller. But on the table tennis balls, we have lots of gaps, whereas with the play pit balls, not so many. So the total volume of gaps in each of the boxes is very similar. If we take it a step further and we mix up the play pit balls and the table tennis balls, we get a mixture of different sizes. And this allows us to pack our spheres more efficiently because the small table tennis balls can fill the gaps between the larger spheres. So we get a mixture like this. You knew that packing of different sizes, or volumes in this case, leads to greater packing. For example, your suitcase at home, what do? You get the big things in first, put your shoes in, and then you get your socks and you squash them into a corner. Okay, so we can go a step further. When we think about ceramic materials, the particles, or powder particles, don't need to be spheres. They can be lots of different shapes. Now, we've exaggerated them here. We've got stars, packing nuggets, I might find a dinosaur. Different particle shapes lead to different packing of materials. And in this case, maybe ceramic materials. We can reduce the size of the gaps if we use different particle sizes and also different particle shapes. 4 different Perspex boxes, different particle shapes, different particle sizes. Very easy to talk about different packing fractions with spheres, or you might even think about different crystal structures related to metals, for example. Gaps in materials can affect their mechanical properties, such as how easy it is to squash something. So here I've got a sponge, and a sponge is filled with lots of different gaps. One of the questions you might want to ask is, can you name what these are? Generally, they're pretty good at doing that. They can say, yeah, this is a sponge, and then you ask them what the gaps are, and they know what they are. What you can then do is you can show them the sponge, and when they squash the sponge, initially, very easy to squash it. But then as they continue to squash the sponge, it becomes more and more difficult. You have to apply more force. You can relate this to the gaps in the material. As you reduce the number of gaps, it's harder to squash the material. The elastic modulus of your material increases. We have a variety of sponges, so allow the people at the stand to get hands-on and give the sponges a squash. With sponges, we can relate the mechanical properties to our model with foam spheres. So, we've got some Perspex discs and also some foam balls. We've also got these little Perspex rings, and these are to indicate gaps in the material. So here we've got 3 foam spheres, and when we squash on the Perspex disc, really easy to squash. Now, if we go from 3 foam spheres to 6, and we fill in the gaps, what do you think happens now? Well, it's much more difficult to squash. This is related to the elastic modulus in our material, which is how easy it is to squash. So as we fill in the gaps, it becomes more difficult to squash. We can relate this model to our sponge. Here we've got our gaps. As we close up the gaps, it becomes harder to squash. Here, 3 foam spheres, squash, really easy. But with 6, much more difficult. Comparing different materials can be done like this. Here we've got our tennis balls, and here are foam balls. So, which one's easier to squash? Well, let's give it a go. Very easy. Ooh, yeah, much more difficult. So, in material science terms, the elastic modulus of the tennis ball is much greater than the foam ball.